Hello guys, welcome back to my channel Gamma Di Gamma. It's been a really long time. I'm making a video because, well, it's Valentine's Day and I have lots of work to do this week. And in a way, this video making is kind of therapeutic for me. You can say it gives my soul a certain sense of entitlement. Well, I'm sure you have your things in life that do the same thing for you, but this is my poison, I guess, or in terms of this is my form of meditation. So with that, I don't know, reflexive introduction, let's get started. I hope you watched the last video because it's going to be necessary for this one. So in the last video, we actually found solutions to the wave equation. So assuming you have a wave equation, we defined the all of like the time sines and cosines by a collective cosine omega t plus initial phase factor phi, which takes into account all the sines and cosines or whatever. And then we had the general solution as a linear combination of sines and cosines, but in space this time. So since you're working in one-dimensional space, at least for now, we can generalize later, and we will. We're gonna have, let me just be consistent with notation. So A here and B over here and A over there. Okay, and if we say plug in time 0, the initial, you're gonna have cosine of phi, which is a constant, which we can like take into these prime constants, and then finally we're gonna have A times A is A prime times cosine of phi plus B times sine of n pi x over L. Please watch the last video where for all of this motivation, because this page is clearly titled the motivated Fourier series. So where does the motivation come from? It comes in the last video. So do check that out. So our main problem is to find this initial condition. And then once we have this in place, we can just multiply a cosine factor, which is time dependent and subject to initial conditions. These guys are subject to boundary conditions, because for here we don't care about the time, they're independent of time. We care about what they're doing in space, what are the boundary conditions. So that's why it's a clearly partial differential equation problem. We have initial conditions and boundary conditions, which make this problem a well-defined one, which sort of there's more rigorous theory that says, you know, why this differential equation has solutions, and uniqueness is guaranteed by initial conditions and boundary conditions of both. Since this second order, we care about the zeroth derivative or the function itself and the first derivative. Now anyways, if we could find this initial form, we could just plug that in and then we'll have the solution for the entire thing. So what we could do, or one way of thinking about this, is assuming you have a string, say string on like fixed support like this, and the line couldn't not be any straighter. If we knew what the initial pluck was, that's y of 0, right? That's, say if you call f of x as y of x 0. If we knew what this initial pluck looked like, the perfect analogy is a guitar string. If we knew how the musicians plucking it, this could be one shape. If it's a sine or some version of the sine, then our life's way easier, because then we know what exactly to set n as. But if we have something like this that doesn't remotely look like a sine or cosine, then our problem just translates to finding, we know what f of x is, right? I mean, this is, you can define a piecewise function that's increasing in this segment from from 0 to say x naught, and then decreasing from x naught to L. But the challenge is actually representing this function as a linear combinations of sines and cosines. So we're gonna sum from 1 to infinity because we don't know what frequency or what the periodicity inside should be. So we just sum over all of them, and then whatever the periodicity is, we can work our way from there. Just one thing to note is that we have no 2 on top here because our interval was from negative L to L last time, so that makes a total length of 2L. In this case, you can say we have negative L over 2 to L over 2, or 0 to L, in which case our interval is now 0 to L. So this 2 doesn't just cancel off. That was originally a 2 because both these functions have a period of 2 pi. So I'm using the same idea of summing over different wavelengths for the sine as well. And now one interesting, curious property rather, is an can really easily be found. It's not so hard. I mean, the integral is hard, but its task just becomes way simpler. Because what you do is you multiply f of x by the exact same factor and then integrate it over the entire interval. So if it's from negative L over 2 to L over 2, you can integrate from negative L over 2 to L over 2 or 0 to L. It doesn't matter. The size should remain the same. For reasons of periodicity, it doesn't matter. And you can do a similar thing for Bn. And it turns out, for the sake of convention, we add an a0 over 2, an initial factor for when x is 0, sine is 0, but the cosine has a 0 term because cosine of 0 is 1. So you do a similar thing for the sine. 2 pi nx over L dx. Now a0 with the similar reasoning becomes 2 over L integral f of x dx. So this sort of becomes twice the average. A0 is twice the average of f of x on this entire interval. How do we get these formulas? It's simple really, because this is a clever observation by Fourier, who first came up with this method, formally at least. Is if you have 2 over L, you integrate 0 to L cosine of 2 pi mx over L cosine 2 pi nx over L dx. And say if you have 2 over L integral from 0 to L sine of 2 pi mx over L sine of 2 pi nx over L dx. Well, turns out both of these actually just evaluate out to give you 1 if m is equal to n and 0 otherwise, which I can write compactly as Kronecker delta mn. So it takes the value 1 when m is equal to n, otherwise it's 0. We use the Kronecker delta really to represent dot products in orthogonal bases. And this should sort of like make sense because we define this integral to sort of be the equivalent of a dot product on the space of square integrable functions. So that's L2 space, which is a space of infinite dimensions because it's spanned by infinite basis vectors. Every function of this form with the n in it, so cosine of 2 pi n x over L is one basis vector, sine of 2 pi n x over L is another basis vector, but since n is going from 1 to infinity, there's an infinite number of these. That's why it's an infinite dimensional space. So this should sort of, I'm just trying to connect this with linear algebra as much as I can because that's the most efficient way of dealing with these problems. And of course, you can integrate this out, check for yourself this result. It's sort of an exercise to you. I hate to say this, it's an exercise to you, but I'm not doing it. It's kind of time consuming and counterproductive for the rest of this video. One interesting thing that we can do with this new gadget, or a better way of representing everything, is y of x, y naught of x, that's initial y of x comma t. Instead of summing from 1 to infinity, sum from negative infinity to infinity and have the coefficient here, e to the I knx, where kn can be 2 pi n over L. So we're using this e to the I something because it compactly represents the sine and the cosine. So if you're interested in a more complex or more general approach to this, this is the way. Well, again, y n tilde, this coefficient that we need to find, is just 1 over L integral from 0 to L y naught of x e to the negative I 2 pi n over L times x dx. And again, you can check the orthogonality condition. So these guys are orthogonality conditions because they sort of work like this, right? Analogous to this. Orthogonality condition here is 1 over L integral from 0 to L e to the I 2 pi mx over L e to the I 2 pi nx over L dx, which is again Kronecker delta mn. You can check this out too. But this is what we're going to sort of use to generate the Fourier transform. Okay, so now time to move on a little bit. What if we have, instead of having the initial waveform defined, if we have, say, a string, and let me do a better job at that. And we know the motion of this particle, the first ever particle, or this end of the string. So assuming it's like driven by an oscillator, so this like oscillator is like rotating around at some frequency, and it's rotating just this end of the particle. So it's this particle's sort of going up and down, or this end sort of going up and down. The other end might be fixed for the sake of boundary conditions. So we know the motion of a reference point. We know the motion of the reference point. We don't know the waveform in this case. So instead of doing a Fourier series on space, we would like to do a Fourier series on time. So all you need to do is just change a few things around. So associated with x, we had, say, the kn. Now associated with t, time, we're going to have omega n. This was the wavelength, this is the frequency. So it's completely analogous in that sense. So y of t at x0, so the motion at the endpoint, we can again write as a naught over 2 sum from n equals 1 to infinity an cosine of omega n t plus bn sine of omega nt, and omega n is 2 pi over capital T, where capital T is now the time period of this oscillator. So whatever this omega driven frequency is, it's 2 pi over omega driven frequency. That's the time period. So instead of having the length or the entire measure of the x, we have the entire measure of time, the time period, capital T. So it's completely analogous in the sense we're not doing anything different or worth noting until now. And then of course we can write f of t as sum from minus infinity to infinity, and use the exponential version of this. And now the Cn factor can be calculated using this orthogonality 1 over 2 integral from 0 to t. So we have a time integral in this case, e to the negative I n 2 pi t over capital T dt, which I will just, for the sake of what's gonna follow, as t over 2, negative t over 2 and t over 2. It doesn't matter, the interval matters, which has a length of capital T in this case. And now what I'm going to do is a redefinition of some sort. So 2 pi n over capital T is omega n. Delta omega is 2 pi over capital T. We're actually going to use a transform, because with Fourier series, what you have is, so this is like 0 to L, right? It mimics the function on 0 to L. Say, let's talk about space first. It mimics the function from 0 to L. And then if you want to like talk of like the function outside this interval, I don't know, just for if you have the entire space, then it's a problem, because it's going to repeat this pattern, because it's constructed from sines and cosines. So it doesn't know better than to repeat itself over this interval. So this is going to repeat, say, from now L to like 2L. So it's going to like keep repeating this way. So it only acts like the function in that small gap, that small interval. It doesn't do that on the entire space because of the periodicity problem. So how do we tackle with this problem? We set the periodicity to go to infinity. So it only repeats itself at infinity, which is never. And that means the time period goes to infinity, which means delta omega actually goes to 0. So these are our continuum limits. And why do I call them continuum? Because the sum's going to turn into integral. Spoiler alert. So we have Cn defined this way. And then we use this definition that we have 1 over t integral with symmetric bounds f of t e to the negative in delta omega of t dt, which is actually going to be 1 over t, say g of omega. G of omega is this integral inside. It's going to be a function of omega. Now f of t is 1 over t sum from n minus infinity to infinity g of omega e to the in delta omega t. This is the inverse Fourier transform, or we're just plugging in this weighting, what we know for the weighting factor by the Fourier transform series. My bad, we're still working in a series. So we have the summation still going on, and then this, by our definition, just is going to be delta omega over 2 pi g of omega e to the in delta omega t. Well, in the limit, this delta omega goes to 0, this goes to 0, and this is also going to 0. So it's actually not all going to 0. It's actually represents a Riemann sum. So f of t, which is 1 over 2 pi integral from minus infinity to infinity of g omega e to the in, or in this case, like we have to absorb the n in, because that was part of the summation. N times delta omega, they sort of get rid of each other in the limit. D omega. This is your inverse Fourier transform, but we're gonna be a little more symmetric about this because we have this 1 over 2 pi factor, right? So we're gonna distribute this over the transform integral and the inverse integral. So this was the inverse, right? So the Fourier transform is g of omega, this original guy here, which we can also convert into a Riemann sum using the same sort of idea. 1 over square root 2 pi integral minus infinity to infinity f of t e to the negative I omega t dt. This is your Fourier transform. G of omega is the Fourier transform of f of t, and f of t is 1 over square root 2 pi. Instead, now we plug in g of omega e to the I omega t dt. This is your inverse Fourier transform, because notice if you sort of plug g of omega into this formula, you have 1 over 2 pi because these square roots just square up and you get the original factor like we had up there. So it really is nice. We're just a little more symmetric about this. Some textbooks will just have a 1 over 2 pi up front like that. And this is nice because g of omega is the appropriate weighting factor that will make f of t aperiodic completely. Like, a better way of saying it is that we know what f of t is. It is an aperiodic function, of course. But instead of just having this small window, if we use this definition of g, then this integral is going to mimic f of t over the entire interval from minus infinity to infinity. So it's essentially f of t itself. It's not f of t on a small interval because we remove periodicity by taking the time period go to infinity. I hope that makes sense. We're gonna do some examples of this. Yeah, there's a slight typo here. This should be omega, because if you have a f of t, you need to integrate over all omega, otherwise you can't generate that t out.